Okay, so you know how we always hear about these like huge national surveys about education? Like they're supposed to give us all these incredible insights into what's going on
Right?
in schools across the country, but like what people don't always talk about is
Yeah.
the statistics behind it all, right? Like how do we actually make sense of
Yeah,
all those numbers?
absolutely. And these massive data sets are really valuable, right? They're like gold mines of information. But
Yeah.
the way the data is actually structured, you've got students in classrooms in schools.
Right.
It creates these statistical links that can really trip us up if we don't handle them carefully.
Exactly. And that is exactly what we're diving into today.
Awesome.
So we've been digging into a really interesting research article
Hey.
from Educational Psychology Review. It's
Okay.
by Wang and their team from 2019.
Great.
And it's all about this idea of incidental second-level dependence
Okay.
in educational survey data, which I know sounds a little jargony, but bear with us.
Yeah, it's a mouthful for sure.
Yeah, it is.
But it's a really important concept.
It is.
Especially if you're someone who is like trying to navigate educational research. Maybe you're,
Right.
getting ready for a presentation.
Yeah.
Maybe you're trying to understand a specific topic or just curious about
Absolutely.
how this data actually gets analyzed.
Yeah.
And what we're going to be talking about today is how the way we statistically model this data, especially when you have these like natural groupings that weren't necessarily the main focus of the study,
Right.
can actually change the conclusions we make.
Yeah. So our mission today is to really understand the implications of this incidental dependence.
Yes.
We're going to explore a couple of different ways researchers approach this in their analysis, and then
Okay.
ultimately how those choices affect how we think about and understand education.
That sounds good. So let's jump right into it.
Yes.
The sort of fundamental issue here is this idea of nested data.
Okay.
So can you kind of just paint a quick picture of what that looks like in the world of education?
Yeah, totally. So think of it like Russian nesting dolls, you know? You've got the individual students, right?
Yeah.
And they're
Yeah.
nested within classrooms.
Right.
Then those classrooms are nested within schools.
Yep.
And you might even have schools nested within districts.
Yeah.
So it's this like inherent hierarchy.
Exactly. And the key point statistically is that students in the same classroom aren't totally independent of each other. They're sharing a teacher, they're sharing a learning environment, they might have very similar experiences.
Right.
So if we ignore that connection,
Yeah.
it can lead to some problems statistically.
Okay, so problems statistically, what kind of problems are we talking about?
So the main one is that if we don't account for this clustering, we tend to underestimate the standard errors of our findings.
Okay.
Now, what that means practically is we might think we have a more precise estimate of the relationships in our data than we actually do.
Got it.
And even more importantly, it increases the chances of us making the wrong conclusion, what statisticians call a type I error or a false positive.
Oh, like a false positive.
Yeah,
where
see,
it's
so
not-
like a smoke detector going off when there's no fire.
Okay.
So basically ignoring this clustering can make our smoke detector go off more often when there's no real fire there.
Right, right. So it's like a false sense of certainty, basically.
Exactly.
Okay, so how does this incidental second-level dependence fit into this whole picture of nested data?
So this is where it gets really interesting.
Uh-huh.
So incidental second-level dependence is when you have this clustering, like we talked about with students in classrooms.
Yeah.
But the classroom level wasn't part of how the study was designed. It wasn't the main focus. It's just a grouping that exists naturally.
Got it.
Figure 1 in the paper actually has a really helpful visual of this.
Okay, so let's say a study wants to randomly pick students from a bunch of different schools.
Right.
And the school is the level that they're really interested in.
Yeah,
But within those schools, of course, those students are also in classrooms.
exactly.
So the researchers weren't specifically trying to look at the differences between classrooms, but those classroom groups are still there in the data.
They are. And a lot of national educational data collection programs work this way.
Okay.
They might randomly select schools and then randomly select students within those schools.
Uh-huh.
But because there's a limited number of classrooms in each school, chances are some of those students they randomly picked
Yeah.
are going to end up being in the same classroom.
Right, of course.
And that shared classroom experience creates this incidental dependence.
Okay, so now researchers have this data that has a little more structure than they originally planned for.
Yeah.
So how do they deal with this?
So the paper talks about two main ways to model this.
Okay, what are they?
So we've got 2-level models and 3-level models.
Okay.
Let's start with the 2-level approach. So with this one, researchers only modeled the levels that were part of their original sampling design.
Got it.
So if they sampled students within schools, Their two-level model would have a student level
Mm-hmm.
and a school level.
Makes sense.
That's it.
Okay, so what happens to those incidental groupings, like the classrooms?
So if there's some information collected at that incidental level, for example, like how many gifted students are in a particular classroom,
Okay.
it often gets included at the lower level,
Okay.
which in our example would be the student level.
Gotcha.
So you're essentially attaching that classroom level characteristic to each individual student in that class.
So you're basically like squashing that classroom level information down into the student level.
Yeah, kinda.
Okay, so what about the three-level models?
Yeah, so three-level models account for all the levels of clustering,
Okay,
whether they were the main focus of the sampling or not.
got it.
So in our classroom example, a three-level model would have the student level, the classroom level,
Okay,
and the school level.
makes sense.
And the paper actually mentions a bunch of researchers who have used three-level models
Okay.
with this data set called the Early Childhood Longitudinal Study Kindergarten, or ECLSK,
ECLSK, got it.
to specifically deal with this classroom-level dependence.
So one approach kind of just acknowledges the intended levels.
Right.
And then the other one takes into account all the levels, even the ones that maybe they weren't initially thinking about.
Exactly.
So the paper uses this ECLSK data as a real-world example.
Yeah,
Can you walk us through that a little bit?
absolutely.
Yeah.
So ECLSK is a great example because it has this structure we were talking about where schools were chosen and then students within those schools.
Okay.
But of course, those kindergartners were in classrooms,
Right.
even though classrooms weren't the main thing they were looking at.
Makes sense.
So the research question they were looking at was trying to understand the relationship between how well kindergartners were reading in the spring
Okay.
and three different factors: how old the students were, the number of gifted students in their classroom,
Mm-hmm.
and then the total number of school days in the year.
Okay, and so those are all measured at different levels, right?
Exactly. You've got student level, classroom level, and school level.
Got it.
And that classroom level factor, the number of gifted students, is the one representing that incidental second level.
Okay, so what happened when they looked at all this with two-level and three-level models?
So table 2 in the paper has the main findings. And what really jumps out is that the standard error for that classroom level factor, the gifted students,
Mm-hmm.
was smaller when they used the two-level model.
Okay, wait, so remind me, why is a smaller standard error a bad thing?
So remember we talked about false positives.
Yeah.
A smaller standard error can make it seem like a factor is statistically significant,
Right.
more often than it really is.
Got it.
And in this case, the significance level for that gifted students factor was just below a certain threshold, 0.01 in the two-level model,
Okay.
but just above it in the three-level model.
So depending on which model a researcher used, they could come to different conclusions
Yeah.
about whether the number of gifted students actually matters.
Yeah, that's a pretty big difference.
Yeah, it is.
What's interesting is that the standard errors for the student's age and the number of school days
Uh-huh.
were very similar
Okay.
in both the two-level and the three-level models,
Okay.
which suggests that this problem of ignoring that classroom level might be most noticeable when you're looking at things measured at that level.
Okay, that makes sense.
What about how the variation in reading scores was explained? Did that look different?
Oh, whoa, that's a good question.
Yeah, so it did. Table 3 shows this.
Okay.
When you ignore the classroom level in a two-level model,
Yeah.
the variation that exists at the classroom level doesn't just disappear.
Right.
It gets spread out across the other levels,
Okay.
in this case, the student and the school.
Okay.
And the paper actually gives some equations that show roughly how that happens.
So it's like if you only use a two-level model, you might get the wrong idea about how much of the difference in those reading scores is due to students versus schools.
Exactly, because it's absorbing some of that classroom level variation.
Right, so you're not getting the full picture.
Right. And the paper also points out that the three-level model actually fit the ECLSK data better overall.
Okay. How did they determine that?
So they use these statistical measures called AIC and BIC.
Okay.
Think of them like penalty scores for a model. They reward models that fit the data well, but penalize them for being too complex.
Okay.
Lower score generally means a better balance, and in this case, the three-level model had a lower score.
So acknowledging that extra layer of classrooms gives you a more accurate picture.
Yeah, it seems that way.
Okay, so this ECLSK data shows some of the pitfalls of not taking into account this incidental dependence.
Yeah.
But they also ran a simulation study, right?
Yes, they did. They wanted to see how this incidental dependence plays out under different conditions.
Okay.
So they did this simulation where they could control things like how many classrooms were in each school,
Okay.
and how much variation there was between classrooms.
Like a virtual experiment.
Exactly.
So what were some of the key takeaways from that?
Well, one important finding was that the estimates of the relationships between the factors and the reading score, what we call the fixed effects,
Uh-huh.
were generally pretty accurate in both the 2-level and the 3-level models.
Okay, so both models were getting the basic story right.
Yeah, for the most part.
So the main issue is still those standard errors.
You got it. The simulation really supported what they found with the ECLSK data.
Okay.
That standard error for that classroom level factor was underestimated in the 2-level model,
Okay.
especially when there were fewer classrooms per school and when there was more variability between those classrooms.
So if classrooms are bigger or if there are big differences between what's happening in different classrooms,
Right.
ignoring that level becomes more problematic.
Exactly.
Okay.
And that underestimation, like we talked about, increases the risk of us thinking there's a real effect when there might not be.
Right. That false positive again?
Exactly. Now, the simulation also showed that the 3-level model did a much better job of accurately estimating the variation at each level. But they did find that the precision of those estimates could go down if you had either very few or a very large number of classrooms within each school.
Interesting. So even the more complex model has limitations.
Yeah, depending on the data.
What about that classroom level variation when it was ignored in the 2-level model?
Yeah, so just like they saw with the ECLSK data, when the classroom level wasn't included, its variation got spread out to the student and school levels.
Okay, so it's not like it disappears, it just gets redistributed.
Right.
Okay, so we've talked about these multi-level models, but the paper also brings up this other technique called generalized estimating equations, or GEE.
Yes.
So can you tell us a little about that and how it's different?
So GE is kind of a different animal. It's what's called a design-based approach,
Okay.
and it deals with this clustered data by focusing on the correlation patterns within those clusters,
Oh.
rather than directly modeling random effects at each level.
So it knows that the data points within a cluster are related, but it handles it in a different way. So what are some of the advantages of using GEE in this kind of situation?
Well, a big one is that it can provide accurate standard errors, even if you don't perfectly get the correlation structure within those clusters,
Right.
right? And it doesn't rely on all the same assumptions about the distribution of those random effects as those multi-level models do.
That sounds pretty handy. Are there any downsides to using GE?
Yeah, so a big one here is that it doesn't let you break down the variance across those different levels
Okay.
because it's not specifically modeling those levels.
Okay.
And the simulation they ran suggested that GE generally needs a larger number of clusters, in this case schools,
Right.
to give you really reliable estimates.
So if your main goal is to understand how much variation is coming from students, classrooms, and schools, GEE is not the right tool.
Right, but if you're mostly interested in the relationships between the variables and how certain we are about those relationships,
Okay.
it can be a good option.
Got it.
And the simulation showed that it did give unbiased standard errors for those regression coefficients.
Okay, so it's another tool in the toolbox.
Exactly.
So to sum it all up, what are some key takeaways from this paper for researchers or for our listener who's trying to understand educational research?
So they give some really practical advice if you're really interested in the impact of those incidental level factors, like that classroom level 1, we talk about the number of gifted students.
Yeah.
They generally suggest going with a 3-level model to avoid underestimating the standard errors.
Okay.
But if you do go with a 2-level model, they recommend considering GEE for more robust standard errors.
So for our listener, if you see something that looks like a significant classroom level effect, but they used a 2-level model,
Right.
maybe take it with a grain of salt.
Exactly.
Okay, what if you really want to understand how the variation in student outcomes breaks down across those levels, student, classroom, school?
Then you definitely need a 3-level model.
Okay.
But they do caution that you have to be aware of how those variance component estimates might be affected if the data isn't perfectly normally distributed.
Right. And what if you're mainly interested in things at the student and school level and you're not so worried about classrooms or breaking down the variance?
Yeah, then a 2-level model is probably good enough.
Okay.
The simulation showed that it can still provide solid estimates for those student and school level effects.
And it's simpler too, right?
Yeah, it is.
Okay, last one. What if your main goal is just understanding the relationships between variables, not really the random effects or variance components?
Yeah, in that case, GEE can be a good choice
Okay.
because it provides unbiased estimates for those relationships, even for those incidental level factors.
So the big takeaway is to choose the right statistical approach for the research questions you're asking.
Absolutely.
So this deep dive into incidental second-level dependence really highlights how important it is to think about the structure of educational data, even those parts that might not have been the original focus.
Yeah, if we ignore that complexity, we could end up with misleading conclusions.
Exactly. Different tools, like this 2-level models, 3-level models, GGE, they all have their strengths and weaknesses. And that's especially true when it comes to understanding how certain we are about the effects of different factors and where that variation is coming from.
Exactly.
So for anyone out there reading or doing research, the key is to carefully consider your research questions
Yes.
and then pick the method that best addresses those questions.
This actually brings up a really interesting point.
Yeah.
So we've been talking about education today, but this issue of incidental clustering, it comes up in other areas too.
Oh, yeah, for sure.
Anytime you've got hierarchical data structures, even if they're not super obvious.
Right.
So think about the data you encounter in your own life or work.
Okay.
Could there be these hidden layers of dependence that might be affecting how you're interpreting that information?
That's a good question.
Yeah, something to think about.
It is. I like that.
Thanks.
Yeah, thanks for joining me.
My pleasure.
This was fun.
It was.
All right, talk to you later.
See you later.